we are doing in continuation only. This is AC, alternating current, we are doing in continuation. The previous lecture we have discussed with you about the LCR series circuit and we calculated the impedance. Today we have to talk about the power in an AC circuit. Of course, with LCR series circuit we are talking. So from your previous knowledge, you can take the help. The formula for power, that is instantaneous power, that is V into I can write E into I. Now when I am talking about AC, alternating current, then the values for this E and I are known to you. This is an LCR series circuit and I am having an AC source with me. This is of course R, here L and C. All these are in series. This is the source, AC source, and the value of E is E naught sine omega t. Now when I am having LCR series circuit with me, then of course the value here for current, yes, that is having some phase difference with the EMF, and that phase difference we have named it as phi. Phi is the phase difference between EMF and current. So if I put these values for EMF and current in this formula for instantaneous power, which is equals to E into I, if I put the value, I'm getting the instantaneous power P, which is equals to E naught I naught sine omega t into sine omega t plus phi. Because we are taking phi as the phase difference between the EMF and the current when I am using the LCR series circuit. Now if I simply use the trigonometry formulas for sine, here's this omega t plus phi, if I open this, I will be getting sine omega t cos phi plus cos omega t sine phi. Now sine omega t, if I multiply with those terms, I am getting on multiplication that power, it is equals to E naught I naught sine square omega t cos phi plus sine omega t cos phi. If you wish, you can write that formula in bracket. Otherwise, you can directly write, open this by your knowledge. Now we are talking about the instantaneous power. If we are saying that it is working for the small time dt, then the work done dw, you can write it as this same value, and work done over the complete cycle is, by integration we are getting small work done. If I integrate over the complete cycle, I will be getting the work done, total work done for this cycle. And you have to do that integration part, beta. Then only you will be getting the answer with you. And I am getting it equals to E naught I naught cos phi into t divided by 2. So I can write this value in terms of the your RMS values of E and I. This way. Because this formula which I have got for average power is E naught I naught divided by 2 cos phi. So I can write it as E naught by root 2 into I naught by root 2 cos phi. It will be giving me the same results. And this I can write it as ERMS or EV. We say RMS or virtual or effective value is meaning is the same. So average power, that is given by EV IV cos phi. And you see that this cos phi, it is termed as power factor. And if I want to find this value of cos phi, this is my previous knowledge diagram with me when I took the VL minus VC, assuming VL greater and VR is in this side, then phi is the angle between this VR and VL minus VC. Or I can replace the values for J, that is equals to square root of R square plus omega L minus 1 upon omega C whole square, XL minus XC whole square. This value cos phi is very important, is known as power vector. Now this is I have done in one go, taking it as a general case. Of course, if you wish, you can work out with the things separately also, that I want to calculate the power for a circuit containing only resistance or only inductor or only capacitor. One method with you is you go with all these steps separately. Then other method with you is we have taken the general case and you can take them as a special cases with you. Like if I am talking about the power in an AC circuit which is containing only the resistor, then we know that current and EMF, they are in same phase. We have studied these equations for resistor circuit. Current and EMF, I am getting they are in same phase, so this phi will be equals to 0. And now if I put the phi equals to 0, then cos phi it is equals to 1. So I am getting P average is given by EV into IV. So this formula for average power you need to keep with you. Either you can work out simply by putting the value of E, I and then work out by solving trigonometry, taking the help of integration and all. Or otherwise do this formula you keep in mind, which you can derive, will be applicable for all the three separate cases also. Now if I am having the power, I am talking about AC circuit with inductor only. Now we have studied here that in case of inductor, that current is lagging behind EMF by an angle of 90 degree. So it means phi it is equals to minus of pi by 2. Now if I put this value of phi here in this equation, P average, I will be getting EV IV into 0. It means average power is 0 in case of the inductor circuit. So again the same thing, that magnetization is there and then demagnetized. In capacitors, this also we have discussed earlier. So you have to put the value of phi, which is equals to again 90 degree. So average power we are getting it equals to 0. So it means you should note that energy dissipated in case of inductor and capacitor is 0. It means no energy or no power is dissipated in inductor and capacitors, and that is the reason we are using these devices, your conductor and capacitor, in various devices we are using, because you can see that power dissipated in these cases is 0. That can be shown graphically also. If they are asking you, you can do the graph plotting also for power variation with time in complete cycle. Again in capacitor also there is, because whatever energy we are getting in charging, that is going to get lost in discharging of the capacitor. So this is another definition with you, that what do you mean by wattless current or ideal current. Now we have this formula with us for power, which is given by EV IV cos phi. Now this IV, if I want to resolve into components, I am getting, if it is making an angle phi with the your EMF, then EV cos phi is in this direction, EV sin phi is in perpendicular to it, and this is the cos phi components only which are giving you the power. So power is generated because of the IV cos phi component, while sin phi is nothing doing. So this component which is not contributing to the power is known as wattless or ideal current. So the component of the current which is not contributing to power is known as wattless current. This is again only qualitative idea is being there in your syllabus. What about the LC oscillations? LC oscillations. I am having an inductor, I am having a capacitor. Capacitor is fully charged. Then the electrostatic energy in the capacitor, that is maximum, which is half CV square. And then when I'm connecting it with an inductor, then this will start discharging, it will start producing the current in this, and as a result of this, magnetic field is going to get produced in this inductor. That magnetic field means, because inductor coil will work as a solenoid, and you can see the magnetization of the inductor will start, and you can see that this electrostatic energy UE is getting converted into UB. So at this time T by 8, we are saying UE, it becomes equals to UB. And further on discharging, when time is this T by 4, then what is happening? This is discharged. Capacitor is discharged. It means electrostatic energy is 0, but UB, magnetic energy, becomes maximum. So it means all the current from here, because of this, now demagnetization of the inductor coil will start working, and because of its demagnetization, this capacitor will start gets charging again. So what is happening again? Because of that, you can see that this is starting this you're charging, and it is getting demagnetized. Earlier it was getting magnetized. So this process of magnetization and demagnetization, it keeps on occurring all the time, and that is going to produce your LC oscillations. This definition, that when a charged capacitor is allowed to discharge through a non-resistive inductor. When a charged capacitor is allowed to discharge through a non-resistive inductor, then electrical oscillations of constant amplitude are produced, which are known as LC oscillations. So LC oscillations, they are produced, they are of constant amplitude, constant frequency, and you should be knowing that this process, energy conservation is again holding good. So oscillations, like you can see, but these are the undamped oscillations are produced. If I work with an ideal situation, if we work with the ideal situations, then only these oscillations, I can say, of constant amplitude and frequency, they are produced. But in reality it is not happening, because your inductor is having some or the other resistance, and because of that resistance, some resistance is there in the inductor, I was saying. So because of that, the actually oscillations, they are damped oscillations. So we can make these oscillations undamped again using tank circuit. To talk about the maintained oscillations, so where energy is getting lost, that can be recovered. If I'm saying that Q is the charge on the capacitor at an instant t, and di by dt, which is of course the rate of change of current, then the equation for L and C you can write, which is given by L di by dt plus Q by C. See, we are getting, of course, I can write in terms of dq by dt. So I'm getting a quadratic in this Q, and you should always, you can always compare these oscillations with the 11th class when we have done the spring motion. Like when we are bringing the spring to the mean position, then back to extreme, and so on, we keep doing. So oscillations we are producing. Similarly, you can say LC oscillations, that type of phenomenon. Of course, you can find the equation for the time period or frequency for such equation, because that is behaving like an SHM. So on comparing with that, I am getting omega, which is equals to 1 upon square root LC. Or I can write the value for the frequency, which is 1 upon 2 pi square root LC. Or similarly, you can write it by time period, simply by comparing this equation with the equation of your SHM. That is, I think you all are aware of. and that was your d2y by dt square plus omega t is equals to 0. And in such cases, acceleration is always opposite to the displacement. So this is the formula which you need to keep in mind for solving the questions whenever there is they are talking about the SHM or the oscillations, LC oscillations, when we are having the inductor and capacitor circuit, as I have shown you. One simple I have taken beta for you people. Reading the question for you. In the given circuit, the capacitance of the capacitor, you have to calculate the capacitance of the capacitor if power factor of the circuit is unity. This is the first part of the question. Resistance is written 10 ohm, inductor is written 200 millihenry, and you have to find the value of the capacitance. Power factor is given. So I should be knowing the formula for the power factor, which is cos phi, which is given by R upon Z. So if cos phi they are saying is unity, means 1, then it means R it is equals to Z. So if R it is equals to Z, then you can write your XL it is equals to XC, because this can only happen, R becomes equals to Z only if XL it is equals to XC. So you can apply this condition, you can put the value for XL which is omega L, for XC also you can put the value which is 1 upon omega C. So on solving we are getting the value of capacitance C which is equals to 1 upon omega square L. Put the value of omega. Omega is given to you in the question. It is given angular frequency of AC is 100 per second. So omega is given to you in the question, and L is also marked here in the diagram. That is 200 millihenry. It means 200 into 10 to the minus 3. Then only you will be getting the result for capacitance in farad. So take care of the units beta, and then you work it out. Now you can give this result in farad, or you can further convert it to give the result in millifarad. This is the first part when I have to find the capacitance. Power factor is given unity, angular frequency is given 100 per second. Second part of this question is you have to calculate the Q factor of this circuit. Now it means you should be aware of the formula for the Q factor. Q factor is equals to 1 upon R square root L upon C. This formula which you should know. Then you can put the values. R is given 10 ohm, L is given again, and C you have calculated in farad, that is 1 upon 2000, because we will be working with the SI units. And then I am getting the Q factor is coming out to be 2. And the third part with you is you have to calculate the average power dissipated in the circuit. Now average power dissipated is equals to Vrms upon R, because you know L and C they are not dissipating any power. So only resistance is going to dissipate the power, and you can find the value of the average power here, which is given by putting the values. I am getting the answer 250 watt. So keep things up to this beta. Thank you everyone.